Hi, I'm Marcel Beck. I'm a PhD student at the University of Hamburg, and I'm working on laser interferometry. And my project is called TabC, and what it is, I'm going to tell you about now. So, I don't think the laser mission needs any further introduction. I just wanted to mention that the mission is quite a bit in the future, about 15 years, and that is the reason why there's a great need for ground support equipment. Like here we have a classical laser testbed, and those are normally made by silicate bonding optical components to an ultra-low expansion base plate. And this is being done by alignment machines, which is not only time-consuming but also really expensive to produce. So what the University of Florida did 2 years ago, they set up an interferometer with off-the-shelf commercial mirror holders and mounted them on an ultra-low expansion base plate, like you can see here on the right picture. And we want to do a similar approach, but we want to even go one step further. And we are doing this with our project TabC. So TabC is a toolset for adjustable picometer-stable interferometers, and it combines an ultra-low expansion base plate and thermally compensated mounts, which are mounted on the base plate using invar inset screws, clamps, and so on. So the advantage of such a setup compared to the glued setup is that it is very easy to set up. You can implement new interferometer ideas very quickly, and also afterwards you can reuse all of your expensive components. So this setup shall provide for the laser mission a quick testbed to quickly evaluate new optomechanics and other components. But in order to be a testbed for the laser mission, we have to be below our 1 picometer per square root hertz requirement. And this we are doing by not only having this TabC project, but also having a setup around it. So we are placing the TabC inside a vacuum chamber and also inside a thermal shield, which will suppress temperature noise. Against seismic noise, we're placing it on a vibration-isolated table and also on a breadboard, which is inside here. Since we're doing a heterodyne interferometer, we have two lasers at 1064 nanometers, and we're using two NPRO lasers from the company Coherent. We also have to take care about cabling, which you can see on the right side. For example, for the photodiodes, the temperature sensors, the laser fibers, and so on. But this is only half of the work, because the other half is setting this up in a lab which is temperature controlled. So here we have our optical table where our TabC project inside the vacuum chamber is sitting on, and we of course need a good laser preparation to first of all get a beat signal and also to clean, for example, laser polarization. So if we have a vacuum chamber, we also need a vacuum pumping system. And I'm not going to go into any detail. I just wanted to point out that we have a square pump, which is our pre-pump, and it is placed in the room next door. And this is to isolate TabC from seismic noise and also to protect the people working in the lab from acoustic noise. We also have a turbo pump, which is just placed below the chamber to even go pump more vacuum and to suppress more temperature noise. And suppressing temperature noise is the right idea. So if we look at our temperature noise, which is our pretty much worst enemy in the low frequency range. So we have our TabC project on the left side, and on the right side we have an amplitude spectral density plot with the laser requirement plotted in. So what we have to do, we have to stay below our requirement. And if we look at our TabC, then we can clearly see that we have two major components which will contribute to temperature noise. And this is one, the zero-low plate, and second, the optomechanics mounted on top. So if we first of all look at our zero low plate and we take some data from a vacuum chamber, so we're taking the temperature noise inside the vacuum chamber, which is not our vacuum chamber, but it is a similar vacuum chamber, and we're expecting to have the same temperature behavior. So by just multiplying this temperature noise with the thermal expansion coefficient of the zero low plate, we end up getting the blue plot, which is below our requirement, and we are fine with our zero low plate. Next, we can look at the optomechanics. So if, for example, a laser beam is coming in from here, then it's splitted at the beam splitter. It is going to a mirror where there is a deviation caused by temperature noise. Then it will introduce a tilt-to-length coupling. And this tilt-to-length coupling will introduce some noise. And if we again multiplying for off-the-shelf commercial mirror holders and the value with the deviation values from the datasheet with our temperature noise, this is where we end up. So for example, so you can clearly see that the pitch is above our requirement, and this is not working out. So we searched around and looked for some new mirror holders, and we found these zero drift mirror holders from Newport. And they're promising to have a 5 times lower deviation by temperature, caused by temperature. And if we are doing the calculation again with the values from the zero drift mirror holders, this is where we end up. So here you can see with the green plot, we are below our requirement, and we are fine for that. Okay, so, but we decided not to order a big zero low plate with all of the drillings first of all. Instead, we built a prototype, which you can see on the left side. So here we have our zero low plate and our optomechanics are mounted on top with the zero drift mirror holders. And here we are measuring the length stability of our prototype. And we are doing this by heterodyne cavity locking, where we compare our prototype cavity with a reference cavity. And this is being done by heterodyne cavity locking. And what exactly this is, we can see in the next picture. So here this is a pretty much a simplified sketch of the whole setup. So what we are doing, we are locking each laser to one cavity. And this is being done by, first of all, interfering those two lasers to get a beat signal. This is measured with a photodiode, half of it, and the other half is coupled into a fiber where it is splitted and then sent into the vacuum chamber, where we are aligning our cavities. And yeah, with our prototype cavity and our reference cavity. So the response is being reflected due to the fiber circulator. It is then going to the photodiode and measured. So the normal cavity response of such a setup can be seen here in blue. And if you're wondering why we're having two peaks, this is because we have two different frequencies because of the two lasers. And yeah, so after we measured the cavity response, it is amplified, then mixed with our beat signal, and afterwards low pass filtered. So mixing and low pass filtering with is pretty much a demodulation of the signal. And so we are demodulating this DC signal and to get the AC signal, which can be seen in red here. And if we are taking a closer look at, for example, at one of the peaks of our response, then you can see here that we have a zero crossing. And so this means that we can get this AC signal and can use it as an error signal because of the zero crossing here. And we just place ourselves at the zero crossing, get our control signal, and yeah, which will be used. So the error signal, which we are getting here, is then sent to a PID controller, and for the controller we are using a red pitaya with the purple software, and so the error signal goes in. With our controller we are getting our control signal, which then allows us to tune the laser frequency, and we are doing this by tuning the piezo of the laser or the temperature of the laser crystal, which is inside here. So what this in total means is that if there's a change in length of our prototype cavity, and this is what we want to measure, then the signal is forwarded to the laser where the frequency is respectively changed. So if there's a change in length, there's a change in frequency, and we are comparing the frequency of laser 1 with laser 2 by the beat signal, which is equal to comparing the length of our prototype cavity with our ultra-stable reference cavity. And if we are tracking the beat signal over time, we are measuring it, then we get our amplitude spectral density plot. And by multiplying this plot, which is in frequency, by the length of the cavity and then dividing it by the laser frequency, we get our displacement noise. Yeah, and this is exactly the experiment we are doing at the moment. So to summarize the whole TabC project, it has been set up from pretty much zero. We ordered all of the components, produced some components with our workshop. The lab is finally finished, so we moved into the lab, and the stability setup. So the experiment which I just showed you has been set up and is just, I would say, 2 weeks away from measuring an error signal. So the next step is, to measure the length stability of this TabC prototype, and if the results are good, which we are hoping, this means that this setup is pretty stable, then we can write hopefully a publication about it, and also order larger zero-dur plates to implement all of our new interferometer ideas. Here are, for example, 3 of them. So at the moment we are just having a prototype in there, but in the future we are planning to build a whole tool set for setting up ultra-stable interferometers. So if you have any question, just write me an email, and thanks for listening.